Hello and welcome to the July update from the TauNet team. And it's the developer call. So I'll pass it over to Karim for his updates this month.
Thank you, Fola, and welcome everyone to the July update for the Tau development team. Let me start with Andrei, who has made some significant progress this month on the Tau testnet architecture. He's in the process of writing pseudocode for the Tau blockchain on a uniquely designed that has been done from the ground up using Tau itself. Additionally, he has enhanced our Telegram channel's spam protection. He's also been working on forum development to ensure a safer and more engaging community platform. On the Tau development side, Lucca has integrated 2 new keywords, sometimes and always. He has also added support for those keywords in the normalizer. And he started working on splitters, which is a unique concept for essentially finding a satisfiable formula which is strictly smaller than another Tau formula. He is currently working on the implementation of the full implementation of splitters algorithm for non-temporal Tau formulas. He's also reviewed the order normal form command in the repo. And as you might have also noticed or seen, is that he's been engaged with the marketing team for recording 2 demos for Tau. He's also answered several technical questions regarding the Tau language coming from the community. David has been working mainly on strong normalizations of Tau formulas. He's experimented with several implementations, which are all variations on the base algorithms designed by Ohad, but in an effort to simplify the implementation and improve performance. He's also started working on another major component of the Tau runtime, which is the solver algorithm. Again, this algorithm and implementations is based on a modified version of the algorithm that was proposed by Ohad in the Tauba paper. He also simplified the implementation of Tau Boolean algebras by using operators defined over the standard variant class in order to reduce redundancies in the code. David has also been actively participating in our weekly Tau testnet design discussions. Last but not least, Tomáš has completed some major tasks in the core Tau language. First, he added checks for well-foundedness of recurrence relations. Then he implemented the calculations of fixed point of recurrence relations, which was a major milestone. And in the process, he has had to implement type inference for recurrence relations. And he integrated all of that work into the REPL command line. He's currently working on further type inference for constants and variables and removing the $ from the recurrence relations offsets. As usual, he's also been fixing issues in the system in general. At the beginning of the month, he fixed an issue with empty lines that were causing parse errors. He's also fixed the REPL history command, and he also fixed the getting, setting, and toggling of all other command options. And he finally added more tests to the parser. That's it for the development team for the month of July. Pass it back to you, Fola.
All right, fantastic. Thank you, Karim. Now I'll pass it over to Tomáš for his more detailed update of his month.
Thank you, Fola, and hello, everyone. This month, I've been working mostly on recurrence relations. I've implemented the type inference for recurrence relation references, so we could simplify syntax and grammar. We don't have to use different syntax for different types of recurrence relations. Tau infers types of definitions itself. I've also added type error handling when there is a mismatch or if it's not possible to infer type of a definition. Most of the time I've been working on calculating fixed point of recurrence relations. This is almost finished. I'm debugging and fixing issues regarding calculation of a fixed point of recurrence relations for Boolean functions, and I'm also reviewing the calculation of a fixed point when there is an actual input in the fixed point called arguments. I've also added a check for recurrence relations if they are well-founded, so we can calculate a fixed point. Then I've spent some time on REPL. I've added instantiation of variables, and I've added help for instantiation and substitution. I fixed several issues. There was an issue with empty input line, which was causing a parse error. I fixed indexing of definitions and their printing. I've also fixed indexing of results in history, and I fixed get, set, and toggle commands, which they were not working, so fix that. And also I've added a feature to our parser and to the TGF. It's a new directive. When we parse tau source, we care only about a few terminals from the parse tree. To remove unneeded terminals, we used the directive trim children terminals, where we listed all parser tree nodes. Those children terminals should be removed from the parse tree. And this list was too long to maintain after every grammar change, so I've added a new directive, trim all terminals except children off. And it's possible to list only parser tree nodes. Those children terminals should be kept in the parse tree, while other terminals are removed. So that's all from me this month. Thank you.
All right, fantastic. Thank you, Tomáš. Now I'll pass it over to Andrei. Take the mic, Andrei, for your update this month.
Hello, everyone. As we continue our journey with Tau, I'm here to share some progress and updates over the past months. Firstly, I've been thoroughly researching the architectures of both Aptos and Solana blockchains. Our goal has been to integrate the best elements of these systems into our Tau network to enhance its capabilities and performance. However, we encountered a significant challenge regarding the use of systems under Apache 2.0 license, which Aptos employs. Unfortunately, we couldn't find a legal pathway to utilize this in our context. Despite this, we are not slowing down. We're exploring alternative solutions to keep our project moving forward, since we have some time until Tau language release. One promising direction has been the Polkadot SDK, software development kit, which offers the flexibility and possibility to quickly assemble the blockchain and implement custom blocks. And I've successfully assembled a custom blockchain using this Polkadot SDK, and I'm now in process of building it. And this approach will allow us to test the core ideas of Tau in practical setting without dedicating years for initial blockchain development. In parallel, I've been crafting a pseudocode for the Tau blockchain. This is not just any pseudocode. It's designed to be written in Tau from the ground up, embodying our vision for a truly unique blockchain system. Additionally, as always, I've been vigilant about enhancing the security across our services and combating spam, ensuring the integrity and safety of our platform. So thank you for your continuous support and enthusiasm. Your engagement is crucial for our success. Stay tuned, stay connected, and keep pushing the boundaries of what you can achieve.
All right, fantastic. Okay, Lucca, over to you for your update this month. Thanks.
Thank you, Fola. So as Karim mentioned, this month I have spent time on integrating the sometimes and always keywords into the Tau language. They basically remove the extra Boolean algebra layer of models of Tau formulas and integrate this layer into the what we call the WFF layer of tau formulas. So what they essentially are temporal quantifiers for our input and output variables. Now, this keywords also, of course, need to be treated correctly in the normalization process. This is something I spent time on this month. And as Karim also mentioned, the next big task after the sometimes and always keywords were introduced was the splitters. And the splitter in logical terms means given a tau formula, find a tau formula that is not zero or not false in this sense, which implies the tau formula we started with. And if you take implication as an ordering, then you get that you want a strictly weaker tau formula, which is satisfiable, which is the wording that Karim used. Furthermore, I've been working on 2 demos for the tau language this month. You can see the videos soon. I think they are not released yet, but we are working on releasing them. In these videos, we feature the basic features which are currently implemented in the tau language so that you can explore the application in more detail. Then I also reviewed the order normal command. There were because I was using this command in my splitters algorithm initially, then I devised a new method which would not rely on this command, but nevertheless it's something that we want to feature in the REPL, and so I made sure that it works correctly in all intended cases, and then I also helped with answering some of the technical tau questions by the community. So just to give a little idea, I have one basic demonstration of the always and sometimes keyword and one basic demonstration for finding the splitter. So this first example shows a basic normalization of the sometimes and always keywords. So we have an output stream which we call O1. We say that it is 0. And as you can see, we have nestings of sometimes and always, disjunctions, conjunctions. And if you work everything out, you will see that this just normalizes as the algorithm also returns to always O1 of t is equal 0. So the takeaway is that nestings of the sometimes and always keywords are denested because they are quantifiers. So the most inner quantifier captures the variables and the other ones are not used. And then the always distributes over conjunction and sometimes distributes over disjunction. Now regarding the second demo for the splitter, so we start with the tau formula x equals 0 and w unequal 0, or y or z, y or z unequal 0. And now a splitter will calculate a weaker formula, and in this case, the most simple thing to do is to just remove the z variable, and so the splitter algorithm in this case returns that the weaker formula, which is still satisfiable, but implies the one we started with, is just x equals 0 and y unequal 0, or y. So the formula that the splitter algorithm in this case returns is x equals 0 and w unequal 0, or y unequal 0. Thank you for listening, and I'll pass it back to Fola.
Thank you very much for your demos, Lucca. Amazing. And now I'll pass it over to David for his update this month.
Thank you, Fola. Hi, everyone. I have spent the month with the following task. I have finished the strong normalization of formulas. To do so, I have made several changes in the implementation that we previously have. The current algorithm differs slightly from the ideas presented in Tava in order to simplify the code and improve the performance. It basically transformed the formula to BDD incrementally and normalized each path of the BDD according to the techniques shown in Tava. I have spec'd out the first implementation of the solver, and I'm writing the test to check that everything is working fine. There are several, let's say, big pieces in the overall structure of the solver. One, to find a solution of an equation, an implementation of LGRS, Leuvenheim General Reproductive System, and iterators to generate all the possible mean terms inequality systems, and let's say the solver that call everything up. So that's more or less an overview of the current algorithm. The way it works is first we remove one equality, and after that we iterate over all the possible mean term systems and try to solve them. Once we solve one, we return the solution. Apart from that, I've been defining logical operators over standard variant, which is let's say the structure that we use to store the constants in the Tau language. With these operators, we could simplify the manipulation of the constants inside the Tau code, and in particular, it simplifies the implementation of the Tau Boolean algebra and also the solver that I was discussing previously. Mainly because instead of extracting the constants, performing the operation, and then reconstructing the nodes that we use in Tau, these operators deal with all that automatically. And apart from that, I have made several fixes and improvements in the code. In particular, I have made several changes into the normalizer in order to allow uninstantiated constants and unresolved recurrence relations when calling the normalizer. And finally, as usual, I have participated in the testnet design discussions. So now, if I'm gonna share my screen to show you how the strong normalization works. Okay, let us show how the strong normalization for WFF formulas work. First of all, I want to show you it's just very simple cases to let's say see what are the basic strong normalizations that we could consider. So regarding trivial cases, if we try to normalize the true formula, we get true, the same for false, or equality, inequality, okay? So those basic formulas, they just, let's say, normalize it ad initio. If we consider a disjunction inside an inequality, we start to get a different formula. In this case, what we are doing is splitting the disjunction into a conjunction and then transforming that into a BDD form. That's why you see that formula, okay? If you have a conjunction, it's in a strong normal form. So all these cases are very simple cases, and you could see how the strong normalization applies to each of them. For more complex cases, let us consider, for example, what happens when we have several literals of the WFF formula which correspond to the same mean term. For example, if we have this formula where we have a couple of a BDD, we are considering constants over BDDs, which is at the end the same as propositional calculus, multiplied by a variable x equal to 0 and another constant y multiplying x conjuncted by x equal to 0, okay? And the solution is the one that you see here. What we are doing is mixing all the constants, okay? And if you see, what we get is more or less the BDD representation of the product, of the disjunct. We could also consider more complex cases where we perform the simplifications using corollary 3.1 from the Taba book to further normalize the formulas. For example, in this case, we have an equality and an inequality, okay? And using corollary 3.1, we are able to further normalize this conjunction, and the result is what you see here. another one. This one is a little more complex. We have another literal, but you see that the idea was fine. And the same if we have disjunctions instead of conjunctions. Yes, in the last case, we are applying another kind of simplification. For example, in the second literal, when we have the BDD x times conjuncted with the BDD y conjuncted by x different from 0, we could see that the second literal implies the first one, because if the second literal is different from 0, then the first one is also different from 0. So we could remove, in this case, the first literal from the formula, and that's what we are doing. Okay, and that's all. That's what we wanted to show you, just so you could get an idea of what the strong normalization is. Thank you very much.
Wow, extremely impressive, David. Thank you so much for showing us the demo. And yeah, really, really amazing stuff. And I'm looking forward to the next steps of Tau language, and the rest of the community are too. Now, and last but not least, I'll pass it over to Ohad to wrap up the developer team call.
So this month, I had some more work on the patent, as well as continuing to work on the network specification abilities, to develop network specification abilities in the Tau language, and ongoing work on releasing the first version of the Tau language and the testnet.
All right, that about wraps it up. Thank you all so much for tuning in, and we'll see you on our socials. That's Twitter or X now, and Telegram. Cheers.